It's the time for introduction of our chief guest. For that, I welcome Mr. Saktivel, Assistant Professor.
associate professors, and assistant professors in the Department of Mechanical Engineering. Dr. U. Ilayarasan has completed his UG degree in BE Mechanical Engineering at St. Joseph College of Engineering and Technology. He completed his PG degree in ME Manufacturing Engineering at Ponnaya Ramajayam College of Engineering and Technology. He completed his master degree in MBA at Alagappa University. He also completed his PhD doctorate in manufacturing engineering at Annamalai University. He has total 6 years experience, in which 3 years experience in research and 3 years experience in teaching. And he also published various papers in international and national journals. His major area of research in non-traditional machining, powder metallurgy, and composite material. He has several professional membership in IAENG, IIOR, and IRED. He published 22 papers in international journals. Also, he published 2 papers in national journals. He published 18 papers in international conference, and also he published 10 papers in national conference. He is awarded National Fellowship by UGC Delhi. Also, he awarded Best Paper in International Conference held at Panimala Institute of Technology, Chennai. He acted as a NBA coordinator. He organized several national conference, international conference, and faculty development program. He is the reviewer of various peer-reviewed journals. He also published 3 book chapters. He visited the University of Malaya, Kuala Lumpur for the international conference and workshop. From which I hand over the session to Mr. Aswin sir. Aswin sir.
Yes, thank you, Saktivel sir. Thanks for your presentation. I need to thank our HOD sir as well as Saktivel sir for their excellent speech. Now it's the time to deliver the session to our chief guest. I request Dr. Ilasan sir to deliver the address, to deliver the presentation. Please, sir.
Okay, sir. Good afternoon, all of you. Most respected Principal Madam, respected Head of the Department of Mechanical Engineering, King's College of Engineering, and Mr. Desikan and Saktivel sir, coordinator of this program. I'm grateful to management of King's College of Engineering for inviting me as a resource person for a one-day webinar. And young and energetic faculty from various engineering college, research scholars, UG and PG students. So I'm going to share my slides. So is it visible, sir?
Yes, sir. Visible, sir. Visible. You can proceed, sir.
Okay. Okay. And Sakil sir introduced about me. I'm Dr. Ilayarasan from Eastern Engineering College, Department of Automobile Engineering, Chennai. So the topic is which is going to be discussed in the further forthcoming slides. surface modification of magnesium alloys using electrical discharge coating. So this we are going to cover surface modification is a very wide area. Within this 1 hour, it is very difficult to cover this topic of this process. And I try to cover basics of this process. Okay. So we go to the next slide. So this is the content of this presentation. So the following content are going to be discussed in the forthcoming slides. Okay, this is a surface modification. This is a very surface modification, very interesting subjects. And then electrical discharge machining, electrical discharge coating, powder metallurgy electrode, advantages of ADC, application of ADC, magnesium alloys, application of magnesium alloy, EDC experiment on magnesium alloy, effect of parameters on the responses, a microstructure analysis, and conclusion. The following contents are going to be discussed in the forthcoming slides. Okay, the modification we know better. Modification is a common word. Okay, so any material, any substance, any object can be modified by using various techniques. So in this presentation, we are only concentrate on surface modification. Okay. So surface modification is act of modifying the surface of any workpiece material in order to improve the properties, such as physical, chemical properties, biological properties. Okay. So why we should modify the surfaces? It is a very important thing. Okay, based on the requirement of application, the surface of the workpieces are modified. Okay, the following contents to be improved by modifying the surfaces: contamination prevention, surface roughness, corrosion and wear protection, adhesion strength, hardness of the workpiece have to be improved, and friction and lubrication performance, electrical and magnetic properties. Okay, the following properties can be improved by modifying the surface. So most of the engineers and researchers are focusing on the some of the engineering material based on applications. So if you want to the surface of the workpiece affected by any environmental condition, some of the researchers are modified the entire workpiece. So no need to modify the entire surface, the entire workpiece. Just if you modify the surface of the workpiece, can enhance the following properties. So surface modification techniques. So any material can be modified using any techniques. Okay, here in this slide I have given surface modification techniques. So there are, it can be classified into 3 methods. Methods: mechanical methods, chemical methods, and physical methods. Machining, grinding, polishing, blasting. These are the comes under mechanical methods. So second methods, chemical methods. In the chemical methods, it has 5 techniques: chemical treatment, sol gel, anodization, CVD, that means chemical vapor deposition, and then biochemical methods. And third one is physical methods. It is also has 4 techniques: spraying, PVD. We know better PVD, that means physical vapor deposition, ion implantation and deposition, glow discharge plasma treatment. Okay, these are various. Apart from that, there are various surface modification techniques are in the engineering society. Okay, we know better. Apart from that, we know plasma spray, thermal spray. These are all comes under spraying technique. We know better. Another one technique is HVOF. Some of the manufacturer engineers know very well. High velocity axi-fuel. It comes under spraying technique. Okay, these are all the surface modification methods. So then coming to the non-traditional machining. So non-traditional machining is the group of process that removes the unwanted material from the workpiece. So during this process, there is no physical contact between the tool and workpieces. Okay. Now in the NTM processes, removes the material by using various energy. You can see there are four energies: mechanical energy, thermal energy, also be used, chemical energy, and electrochemical energy. So NTM process based on energies. So I have given, as discussed in previous slides, I have given four energies. Based on energies, some of the NTM process machinings are working. And mechanical energy process, there are four processes: ultrasonic machining, water jet cutting, abrasive water jet cutting, abrasive jet machining. This under mechanical energy. And then electrochemical machining, the ECM, very important process in NTM processes. And the electrochemical deburring and electrochemical grinding, these are all comes under electrochemical process. And then thermal energy, so electrical discharge machining. Electrical discharge machining is one of the well acknowledged machining process in NTM process. Most of the research engineers and scientists are focusing on the particular machines. By using this machine, we can enhance the material removal rate. Most of the industry, automobile and aeronautical and biomedical application industry are using this EDM processes. Electrical discharge cutting, as electrical discharge cutting is one of the EDM process, and that process, EDM process, they are using electrode. In electrical discharge wire cutting machine, wire cutting, they are using wire for making intricate shape can be done by using this method. And the electron beam machining, laser beam machining, plasma arc machining, conventional thermal cutting processes. This five process comes under thermal energy processes. Finally, chemical processes. Chemical process means there is no chemical reaction between the workpieces and some of the chemicals. Chemical milling and chemical blanking. These are all the chemical processes. So in this slide, I have given some of the NPM processes, the widely used in the applications. Here, ultrasonic machining, electron beam machining, electrical discharge machining, and abrasive jet machining, water jet machining, and laser beam machining. So each and every machining process uses some of energies as discussed in previous slides. Okay. Next. So electrical discharge machining is a very important machining process in NTM. Okay, widely used in the various applications to remove the unwanted material from the workpiece. Okay, during the process, already said in above, in each and every NTM process, there is no physical contact between the electrode and workpieces. It removes the material by series of electric sparks supplied between the electrode and workpiece. And also in the slide, I have given the schematic diagram of electrical discharge machining. It's a positive terminal, negative positive terminal connected with the workpiece, negative terminal connected with the electrode, and there will be a servo motor, tool electrodes, dielectric tank. Dielectric tank, it is a very huge size tank, and the dielectric fluid filled with this, and then dielectric, various dielectric used during EDM process. And mainly, like dielectric fluids are hydrocarbon oil, EDM oil, and also acted as a dielectric during EDM process. And the inter-electrode gap is a very important. There is a distance between the electrode and workpiece. This is an inter-electrode gap. By controlling, and this is electrode gap, it moves up and down direction. By controlling the inter-electrode gap distance, can be control the machining performance, the workpiece and fixtures. Okay. Then so EDM parameters while machining. So when machining the any one hard material, and the two parameters can be controlled. So in this research, electrical EDM parameters can be classified into two parameters: an electrical parameters, and another one is non-electrical parameters. Electrical parameters, there are several parameters, like you can see in the slide: the discharge current, discharge voltage, pulse on time, pulse off time, duty factor, and polarity. These are all the electrical parameters. And the other side, non-electrical parameters are also given. Types of electrode, which kind of electrodes we are using, And there are several types of electrode we can discuss in the forthcoming slides. Inter-electrode gap distance, very, very important during EDM process. Flushing pressure means pressure of dielectric fluid during the machining process, how much pressure we are supplying during the machining. And then types of dielectric, already discussed. Types of dielectric means what kerosene or dielectric EDM oil or hydrocarbon oil. And then concentration of dielectric, this is mainly based on the pH levels of such dielectric fluids. Okay, these are types of electrode. These are following electrodes were used for EDM or EDC. So there are two types of electrodes. Okay, these are what are the types we can see. Conventional electrode and powder metallurgy electrode. The conventional electrode, there are 4 electrodes are there. We know better. The pure copper electrode, which is the copper electrode is manufactured by the pure copper material only. And then brass electrode, aluminum electrode, and tungsten electrode. These are all the conventional electrode. The following electrodes are used for machining the material. Among the 4 electrodes, copper electrode is a very, very important electrode all over machining process, because the copper electrode has a high thermal and electrical conductivity. Compared with the other 3 electrodes, copper electrode has improved the material removal rate and surface roughness, etc. So these are all one of the modification techniques. And coming to the second, the powder metallurgy electrode is a very, very important. This is related to our presentation. Let's take powder metallurgy electrode. Please keep in your mind, powder metallurgy electrode, very, very important. This is used for coating or deposition of the material. Okay, this powder metallurgy electrode is prepared by the 2 or more combination of metal powders. Okay, we can take here I have given the some of the composite electrodes prepared using different materials. Copper, tungsten carbide, cobalt composite electrode. This is a composite electrode means otherwise we can call it as a powder metallurgy electrode. Okay, composite electrode. Okay, tungsten and copper electrode, tungsten and nickel electrode, and tungsten and copper and tungsten disulfide electrode, and copper and copper mixed with titanium electrodes. These are all the following electrodes are chosen based on the literature studied before the presentation. Okay, I have referred these some of the journals, published articles. They are using this following electrodes, composite electrodes, for the EDC process. So, and conventional machining process, conventional electrodes are using for machining purpose only. Powder metallurgy electrodes are coating purpose only. This keep in your mind. Okay, the parameters involved during the electrode preparation. So, electrode has been prepared. Electrode has been prepared based on the. Sir, please once again, sir. Sorry for the disturbance.
No problem, sir. You can proceed. No problem. No problem.
Parameters involved during the electrode preparation. Okay. During the electrode preparation, there will be some of the parameters: particle size, compaction load, composition, density, and sintering temperature. These are the very important factors during the electrode preparation. So, if a particle size, if we increase the particle size of the workpiece, the compaction will be differ. Okay, and then compaction load, while compacting the electrode, pressure will be applied during the electrode preparation. And the composition, very important factors. Proportion of the electrode powders, we can take it as 50-50 ratio and 70-30 ratio. We can take it. The density of the composite electrode. Okay, based on the load applied during the electrode preparation, the density of the composite electrode will be controlled. Okay, and then sintering temperature. After compacted the electrode, this there will be a green compactor. Okay, after if you want to increase the bonding strength of these such electrodes, the sintering temperature is very, very important. Okay, if sinter the electrode, we can enhance the bonding strength of the electrode. Further, we can use to EDC process. So, electrical discharge coating. So, this is the main topic of our presentation. So, electrical discharge coating is the mass transfer process of EDM, while recently used for create the uniform coating on the workpiece surface by series of electric spark, and also which is used for to enhance the tribological properties of such as micro hardness, wear resistance, corrosion resistance without any physical changes of workpiece material. So we know better the EDM only. Some of the research only know the. Some of the faculty members are here and PG, UG students and UG. I think 6th and 7th semester. And the UG students will study. Okay, AD unconventional meshing process. This is one of the process EDM. So only know when EDM only they know, and this comes electric discharge coating is one of the process of EDM. Okay, by changing the polarity of EDM machine. The EDM is a positive polarity, the machining will be occur. The negative polarity, the electric discharge coating will be created, okay, over the surface. So main aspect of EDM is surface modification by transferring the electrode material over the workpiece. It's commonly known as electrical discharge coating. So mechanism of EDC. So we know EDM. There's a mechanism of EDC. Electrical discharge coating is a surface deposition process in EDM for creating the uniform hard and wear resistance coating on the workpiece surface using powder metallurgy electrode. Okay, already discussed. By passing the current between the electrode and workpiece, this ionization temperature will be produced. When ionization temperature 8000 Kelvin will reach, what happened? The melting and vaporization has been take place in between the electrode and workpiece. So high quantity of material has been removed from the electrode and deposited over the surface. This is electrical discharge coating. Okay, so here I have given the schematic diagram of EDC, which is prepared by me. And here in this process, tungsten carbide copper composite electrode are used. Servo and power supplies there will be there, and dielectric fluid, the tank, and tungsten copper composite layer has been formed over the surface, and toolless cathode and workpiece as anode. The schematic diagram. The difference between the EDM and the EDC. So some of the researchers they don't know, and the UG and PG students, you can see the difference. What's the EDM and the EDC? Electrical discharge machining. What is the electrical discharge coating? Definition based, and EDM is a material removal process first, and EDC is a metal coating process. Okay, to achieve the some of the properties. Both are the modification techniques. Oh, yes, I have given the slide for the difference. Okay, and then electrode polarity, and the tool electrode or tool can be placed in either positive or negative terminal, depend on the parametric condition. Here the positive terminal, tool as a positive terminal, and workpiece as a negative terminal. Okay. Weight of the workpiece after processing, better. After machining, some of the material has been removed from the workpiece, so the material weight is reduced. So decreased due to the material removal has been take place. The EDC process, after coating, the electrode material will be removed and deposited over the surface, so that the weight of the workpiece has been improved. So that EDC, okay, function to remove the material from the workpiece, here to enhance the surface properties of the workpiece. So what are the response can be achieved during the both process? In the EDM process, material removal rate can be improved, surface roughness can be maintained as a mirror glass roughness. Here EDC process, material deposition rate, surface roughness, layer thickness, and micro hardness, okay, can be achieved by using this EDC process. Okay, and then characteristics of EDC. So what are the characteristics can be achieved by EDC technique? Materials deposition rate, surface roughness, layer thickness, layer composition, micro hardness, tool wear rate, corrosion resistance, wear resistance can be achieved by using these techniques. Advantages of EDC. So it has some of the advantages. EDC less expensive. So compared with other techniques, if you want to use other techniques, you need a special apparatus to control some of the coating techniques. Here in this EDC process, no need to use a special apparatus. By using ordinary EDM machine can be enhanced the surface properties. So, and then coating can be created in different zone of the workpiece. Okay, with less expensive. It's a very, very important, so that EDC is widely used in this several processes. Limitation of EDC. So even it has a several range of advantages, and also it has some limitations, advantages, so it should be electrically conductive material. So when you choose the material, both the electrode material and the workpiece material should be electrically conductive, so that we can use. So slow process, particularly if you need a good surface finish and high accuracy are required. Okay. A dielectric vapor can be dangerous. It is a very important during this process. We have to maintain some distance during EDM process. Heat affected zone near cutting edges. This is one of the main drawback. And die sinking tool life is limited. Okay. And we want to, this is a consumable, and the tool means consumable. Frequently, we have to change the tool. So application of EDC. So it is a widely applied process. Even it is most of the researchers are focusing on the EDC compared with other techniques. The industrial application based, biomedical application based, they are using the EDC techniques. So EDC can modify the surface of various manufacturing equipments like mold, dies, and drills. In the roll texturing and roll covering by improving the wear resistance is also used, and repair the own region of the workpiece by coating them, by coating the protective layer, okay, to protect you from the other environmental conditions, okay. And then biomedical applications, these following, I have given the 4 points. The biomedical application based, I have given 4 points. The points are taken from the previous published research articles, which is indexed in highly reputed journals. Okay, the biomedical EDC technology applied in the several techniques. Thick and porous oxide layer on the biomedical TI implant surfaces to enhance the growth of the tissues. It's very, very important. It is a biomedical application based. It is widely applied. EDC techniques is growth of the bone tissues and accelerating the healing. Okay. And then another researchers are improved the biocompatibility of the titanium alloy to human bone and teeth by depositing the such layer to enhance the corrosion resistance of beta-based aluminum alloy, titanium alloy, which is widely used for the orthopedic and dental implants. So biocompatibility. So can you hear me, sir? Hello.
Yes, sir. Audible, sir.
Oh, okay, sir, okay. Okay, thank you. To enhance the corrosion resistance of beta-based titanium alloy, which is widely used for orthopedic applications like dental implant. Okay, biocompatibility of the artificial implants can be improved with the cell attachment and proliferation. Okay, these are the important applications. Okay, most of the researchers focusing on that particular techniques to improve the biomedical properties. Okay, history of EDM and EDC. Actually, in 1770, the EDM was introduced, and from 1770, 1930, from year-wise. In 2010, the electrical discharge coating has been implemented. Okay, the past 10 years, it has been being developing. It's a process going. The most of the IITs and the NITs are focusing on the EDC process to improve the surface properties. Very important. Okay. And in this 2013, carbon nanofiber and assisted micro EDM of hard ceramics. 2014, so they are trying a dry EDC process. 2015, powder mixed EDM. 2016, suitable dielectric fluid in EDM process. In 2020, up to research eco-friendly of EDM for surface modification. You can see in 2020, they are using EDM for surface modification process. In this regard, accordingly, I have chosen this EDM process for a surface modification processes. So comparison of EDC with other coating techniques, you can see I have given the 5 points now. Working environment, this both EDC process. I compare with the EDC, thermal spraying and electroplating like this. One working environment I have given room temperature. The both are these are room temperature, workpiece and coating material. For the EDC process, both the workpiece material and coating material should be electrical conductive material. For I have given for thermal spraying, workpiece any material and coating material should be in metals, alloys, carbides, ceramics, and polymers. And for electroplating, workpiece material should be in electrical conductive material and coating material should be metals ions. And the coating efficiency is also given here. And compared with the thermal spraying and electroplating, EDC very high. Comparatively, thermal spraying also high, but electroplating is intermediate coating. Okay, so medium. And function of coating, the hardness, roughness, corrosion, and wear resistance can be improved. Here, for thermal spraying, wear resistance and corrosion resistance can be improved. Electroplating resists the wear, corrosion, high electrical conductivity and reflectivity. application, and also I have given some of the application: biocompatible implantation, mold and dye industry. Here also thermal spraying, aircraft engine parts, storage or car tanks like this and all, and then electroplating techniques, electronic industry, waste industry, they are using the some of the applications. Okay. So magnesium alloy. Coming to the main alloys in our topic. Okay, this magnesium alloy is a lightweight structural material widely used in the various applications, particularly in automobile and the aerospace applications. 30 to 40% of magnesium alloys are widely used in the automobile and aerospace application. We know better because a lightweight, high strength compared with aluminum. Okay, it is used in the aerospace and automobile industry for fabricating the parts. Okay, density based, it is 35% lesser than the aluminum and 61% lighter than the titanium. Okay, density based. So types of magnesium alloy. Okay, magnesium alloy we know better. It's a lightweight material I discussed in previous slide. Okay, this we can classify it into two types. Okay, wrought alloy and cast alloy. So wrought alloy means I have given some of the alloys comes under wrought alloys. A is at 10A, 10A, A is at 31B, A is at 61A, like this. And the cast alloy, A is at 63A, A is at 81B, this like this. Okay, the cast alloy. So we can see the forthcoming slides. So what is wrought alloy? What is cast alloy? Okay. So magnesium alloy, wrought alloys. Wrought magnesium alloys have been manufactured in the form of rolled plates and sheets, extruded boards, rods, tubes, and forged shapes. In the cold condition, ductility of the wrought magnesium alloy is very low. Hence, alloys are worked at hot temperature within the range of 300 to 475 degrees centigrade. Okay. What is the wrought magnesium and manganese alloy cannot be subjected to the heat treatment. The wrought magnesium alloy and aluminum zinc alloys, I have given some of the A, Z. So A denote aluminum, Z denotes zinc. Okay, so that what's the 10? You know very well. A means aluminum 1%. C, Z means 0. Okay, there is no zinc materials. And then wrought magnesium, zinc, zirconium, and thorium alloys. I have given some of the material here. So then the cast magnesium alloy. Cast magnesium alloy is a very, very important material widely used in the various engineering applications, and which is manufactured by the casting methods such as alloys are manufactured through permanent mold casting, sand casting, and die casting. Mechanical properties of magnesium alloy are lower than the wrought alloys. Okay, the most of the cast alloys used in the several applications. So I have given some of the composition: cast magnesium, aluminum, manganese alloys, the AM100A, and then cast magnesium, aluminum, zinc alloys, and cast magnesium rare earth. This is a very, very important. Most of the engineering field are using this kind of alloys. Some zinc, zirconium alloys, cast magnesium, and thorium, zirconium alloys like. So properties of magnesium alloy here, I have given the 4 properties: lightweight, low density, better, 2/3 than that of aluminum, good high temperature resistance and mechanical property, good. This is very good to excellent corrosion resistance. Okay, one of the main drawback of this magnesium alloy is wear resistance only. So advantages of it has some of the advantages for magnesium alloy: lightweight and lowest density, high specific strength, good castability, suitable for high pressure die casting, good machinability, high thermal conductivity, high dimensional stability, higher vibration absorptions. These are all the main advantages of the magnesium alloys. Here it has some of the applications where it is magnesium alloy used: the cylinder head cover, engine intake manifold, motorcycle wheels, helicopter gearboxes, key lock housing, steering wheel. Apart from that, they are using magnesium alloy wide range of properties, wide range of applications. So here I have given some of the applications related to the magnesium alloy, the engine casing. So see, you can see this application of magnesium alloy. This very used various application, various components. So I have given this slide some of the application here. So So these are all the, before we discussed nearly 30 slides. These are basics of process and magnesium alloys. After that, we are going to discuss about some of the experiment has been done by me for research purpose. Okay, surface modification of magnesium alloy using electrical discharge coating. So before that, I have told some of the introduction about the process and the materials. Hereafter, we are going to some research modification of magnesium alloy carried out by me. Okay, this is a material selection, and this is one of the magnesium alloy. Base material ZE41A magnesium alloy. You know better, ZE41A magnesium alloy. What is Z means zinc, E means rare earth. Okay, rare earth is zinc 4%, rare earth 1%. A is a first series of magnesium alloy. Okay, this is here workpiece used for our research. Okay, this is a dimensional 170 mm, 50 mm breadth and 5 mm thickness. ZE41A magnesium alloy has been used. Here the chemical composition of this ZE41A magnesium alloy has been given. So here in this composition, there is zinc is a 3.80%. So in this, there is several composition: copper, silicon, zinc, zirconium, iron. TRE means rare earth. Okay, rare earth, TRE. Nickel and manganese and aluminum and magnesium. So among different composition, which one is higher range? 3.80. Zinc is a 3.80, and the another range 1.18 rare earth. So that this material is ZE41A. Okay, 3.80, the rounded value 4. That rare earth 1.18, the rounded value 1. So that here the 4 ZE41A magnesium alloy. Okay, you can understand. Similarly, the following previous discussed materials also denoted like that. Here properties of ZE41A magnesium alloy. Here some of the properties: density, melting point, specific heat, thermal conductivity, and coefficient of thermal expansion. Okay, this is the lowest density 1.9. The melting point also given nearly 630 degree centigrade. Okay, specific heat also given, thermal conductivity and coefficient of thermal expansion. So for EDC process, material selection is okay, and then the electrode materials. So what are the electrode? There are several electrode materials. So in the process, I have chosen 2 electrode materials. One is tungsten carbide, another one is copper. So they are using tungsten copper here. Here using tungsten carbide and coppers. Okay, so the properties of the tungsten carbide and the copper materials also given here. Materials: tungsten carbide and copper. Density also given. Melting point, specific heat, thermal conductivity, coefficient of thermal expansion, particle sizes also given. So the each tungsten carbide and copper powder sizes, particle sizes 4 microns. So experimental planning and procedures. So before conducting experiment, first we have to prepare the powder metallurgy electrode by the different proportion. Okay, here I have selected 2 proportions: 50-50 and 70-30 proportions. Tungsten carbide 50% and copper 50%, and the another proportion tungsten carbide 70% and copper 30%. So if you take 100 grams total weight, 50 grams tungsten carbide, 50 grams copper. Another proportion 70 grams tungsten carbide and 30 grams copper. Okay, the electrode prepared using powder metallurgy technique. After prepared electrode, the electrodes are sintered using tubular furnace with argon inert atmosphere. So after sintered the electrodes are subjected to the EDC process by various conditions. So electrode preparation, you can see in this slide. The electrodes are prepared using the different metal powders. You know, here during the compaction, different compaction loads are applied: 150 megapascal, 175 megapascal, and 200 megapascal. The holding time of the compaction is 2 minutes. Here I have given the manual hydraulic press. You can see in this slide. See cursor movement. You can see this manual hydraulic press with the highest load capacity is 50 tons. Okay, which is available in Annamalai University. And these are electrodes. The electrodes prepared using in the punch and die setup. Here the lower punch, upper punch, and die. Okay, so the electrodes are prepared by different metal powders. Different metal powder means copper and tungsten metal powders. Okay, this is prepared electrodes. So after prepared electrode, the sintering has been made. Okay, here the sintering temperature is 600 degrees Celsius. The furnace type, tubular furnace, which is also available in Namada University. Vacuum argon gas has been used. The sintering time is 20 minutes. Okay, after sintering, we cannot take it compacted electrode easily from the furnace, and it should be cooled in the cooled it from a furnace itself. Okay, for some times, for 3 to 4 hours. Okay, after that we can take it electrode from the furnace and the airtight cover, packed in airtight cover. Further, you can use to EDC process. So parameters and the levels during EDM. So most of the researchers selecting the parameters from electrical parameters only. So for the EDC process, most of the researchers and scientists are selected the parameters, 2 parameters from electrical and 1 parameter from parameters controlled during the electrode preparation. So I have selected the 1 non-electrical electrode parameters and 2 electrical parameters. So convection load is a non-electrical parameters which is used for preparing the electrode, and the current and pulse on time. Okay. So I have given the 3 ranges, which has been 3 levels, which has 3 levels. 150 megapascal, 175 megapascal, and 200 megapascal. And current range is 2 ampere, 3 ampere, 4 ampere, and pulse on time 50 microseconds, 70 microseconds, and 90 microseconds. So design tool used for this research is central composite design of response surface methodology. Matrix is 3x3 matrix. Total experiment, 20 experiments are conducted to carry out the research to identify the some of the property. Okay, EDC experiment. Okay, this is here. I have given some of the EDM machines, which is a 5530. Okay, EDM E series machines, which is available in Sri Priya Tools, Chennai. Oh, dielectric fluid used for this process is EDM oil, and measuring time for each experiment is 10 minutes. The current ranges I have already given in the previous slide, and pulse and also pulse on time range is also given in the previous slide. Okay, the next. So measuring equipments, both measuring equipments are used for our study. Weighing machine SF400D, weighing machine used for measuring the material deposition rate. So how to calculate the material deposition rate is before and after weight of the workpiece. So before conducting experiment, we have to weighing the workpiece and electrodes. And after conducting experiment, then we have to weighing the workpiece and electrodes. What is the difference between the before and after EDC? The difference is material deposition rate. And also the deposited workpiece has been analyzed using a surface roughness tester to measure the surface roughness value. It is a non-contact surface roughness tester used, which is available also in Namada University, a TR100 surface roughness tester. Okay, these are equipments. So surface coated by EDC. So these are some of the workpiece has been, the deposited workpiece has been given in this slide. So in the right side of the, I have given the 9 parameters conditions as given. The first parameters 150 megapascal, 2 amps, and 50 microseconds. So respected workpiece surface are given in the slide A, B, C, D, E, F, G, H, I. Also corresponding parameters has been given in the right side of the slides. You can see. Okay, wear test. After conducted coating, wear test has been conducted, which is also available in our research lab. And wear testing machine, pin and disc apparatus has been used for conducting wear test, and disc EN31 steel manufactured by disc. Okay, pin size of the pin size as of the coated surface is 20 mm length and 10 mm diameter. And for conducting Takuchi technique, L9 Takuchi orthogonal array has been used. Okay, to conduct the experiment. Okay, then result and discussion. So it's a very important topic, result and discussion. The microstructure of initial microstructure has been given for ZT41 magnesium alloy and tungsten carbide copper deposited surfaces. Okay, in this ZT41 magnesium alloy, the uniform distribution has been made in this microstructure. Here, the microstructure of tungsten carbide copper deposited surface. After coating, the surfaces were analyzed using scanning electron microscope. Here, some of the globules were formed in this microstructure. So which greatly affects the micro hardness and surface roughness. So some of the slides you can cursor movement you can see. See here this globules and some of bigger craters here, some of the craters formed here. So it greatly affects the micro hardness and surface roughness. If the size of the globules and craters will be increased, the micro hardness and surface roughness will be reduced. Okay, then resultant discussion. So after coating, EDS analysis is very, very important. Okay, energy dispersive spectroscope analysis. So which is used for identify the elements presented over the surface of the workpiece during EDM. So this surface is assessed, analyzed by the EDS analysis. So corresponding subject layer thickness has been identified. So the two different places has been take place. One place is 80.77 micrometer, and another one is another one side 103.470 micrometer. So average value has been considered in this study. So material presence here also EDS analysis, which is the surface deposited at 150 megapascal, 4 amps and 90 microseconds. Okay, here some of the electrode materials presented over the surface of the workpiece is confirmed by the EDS analysis. It is a very, very important study in this research. Okay, magnesium, manganese, ferrous, nickel, copper, zinc and tungstens also presented in the surface, deposited surface. So effect of compaction load on MDR, layer thickness and micro hardness. MDR means material deposition rate, how much of material eroded from the electrode and deposited over the surface, which is assessed by the MDR. Okay, so here what happened, at the lowest you can see the cursor movement, at lowest compaction load the material deposition rate is very high. So further increase the compaction load, the material deposition rate drastically decreased, because at low compaction load the density of the prepared electrode will be very low, would be low. So when supply the current which erodes the high quantity of material from the electrode and deposited the workpiece. Further increase the compaction load, the density of the electrode will be drastically increased. So if the higher electrode prepared at a higher density electrode, the material deposition rate is very low. Similarly, layer thickness, if higher deposition is migration rate is occurred, the layer thickness will be high. Normally we know better. And micro, where it is highest layer thickness will be occurred, that the place the micro hardness will be high. So it's a normal. Okay. The coating thickness decreases with the decrease in migration rate. Thus layer thickness and micro hardness values also decreases. The hardness of the deposited surface increased due to the high quantity of material deposition. The large amount of carbon content mixed with the tungsten deposited on the workpiece that offered higher hardness to the substrate. So another parameters, effect of current on material deposition rate, layer thickness and the micro hardness. Here current increases, material migration rate, layer thickness and the micro hardness values increases gradually, because at lower current the discharge spark will be produced in the workpiece and in between the electrode and workpiece will be very low. It is not sufficient to make the electrode material, so the very tiny amount of electrode material discharged from the electrode and deposited over the surface. Further increase the current, the energy, the spark intensity will be very high, so that which melts the high quantity of material, remove the workpiece and deposit over the surface. The both cases are same. Okay, we are mainly we should concentrate on the material migration rate. If material migration rate is high, the layer thickness, micro hardness will be high. Material migration rate is low, the layer thickness and the material micro hardness will be very low. It's a basic concepts. Okay. Here also some of the mechanism also given here. The MMR, LT and MH increases with increase in current. At 2 amps, the discharge spark produced in the machining zone is very low. That is insufficient. That produce the insufficient local temperature in between the electrode and workpiece. So that which erodes the minimum quantity of material from the electrode and deposit over the surface. At a higher current, large amount of electrode material melted from the electrode and deposited over the surface. And also this develops the uncontrolled metal transfer. Okay. An addition of tungsten carbide in the electrode increases the carbon percentage in the deposited surface. That improves the layer thickness but reduce the bonding strength. Here I have given pulse on time on MDR, LT, and MH. Here also, at lowest pulse on time, material migration rate is very low, because at low pulse on time, the produced plasma channel, the diameter of the plasma channel will be very small. Okay, plasma channel means the size of the flame. Okay, very small, which is not sufficient. This here also, so which produces the discharge energy and discharge of the intensity. So spark density, these are the producers. So based on that mechanisms, the electrodes has been melted from the electrode. Here at low pulse on time, low migration rate, here low thickness and low micro hardness. Further increases more pulse on time, more quantity of material crumbles from the electrode and deposited over the surface. So that if higher migration rate achieved, the layer thickness will be achieved, can be improved, and also micro hardness also improved. Okay, so the pulse on time means the time interval of spark produced during the coating that controls the temperature generated in the machining gap. If pulse on time is high, the produced spark density will be high, that erodes the large amount of material from the electrode. Okay, at a high pulse on time, for example 90 microseconds, the diameter of the plasma channel is high, so that removes the high quantity of material from the electrode. Okay, LT and MH increases with increase in pulse on time due to its local temperature produced for longer time in the coating zone. Okay, so coming to the finally, it comes to conclusion. In this paper presentation, tungsten carbide copper composite coating was developed using electrical discharge coating on the ZD41 magnesium alloy very successfully. Different parameters has been studied, and from the microstructure graph, several mechanisms like globules and craters, cracks were formed. The highest coating thickness, 91.6 micrometer, has been achieved in this study. Okay, it was studied that effect plot MMR and LT MH increases with increase in the parameters, in increasing current and pulse on time at low convection load. Conversely, it decreased at high convection load with low current and pulse on time. Okay, so different surface defects has been identified in the semi image. Okay, you can see in the semi image there are several globules, craters, and cracks will be observed. The bigger craters were observed at the surface deposited at higher current. Lower current exhibits smooth surface roughness. Okay, the lower pulse on time, 50 microseconds, developed the small sized globules that made the surface rough smoothly, and also developed the numerous globules on the surface that reduced the hardness. So in my opinion, the EDC technique was suitable for improving the layer thickness and the micro hardness in order to increase the tribological properties. So it is a very interesting subject. Past 10 years it is being developed. So my research also in this process, EDC process. So you can see I have published some of the articles which is indexed in SCI and Clarivative Analytics, very highly indexed journals. The Materials Research Express in the year 2018 I have published, and I have given some of the research articles, 6 research articles which is indexed in SCA. So another journal, Metallurgical Research and Technology, and also been published. Okay, an investigation on electrical discharge metal matrix coating of ZD420 magnesium alloy. Here some same papers in the 2019. A microstructure study has also been carried out in this study using a semi-sintered and the sintered electrode. And achieves of metallurgy and materials also published in 2021 recently. Here also 2021 effect of parameters on microstructure study also being carried out and published. And then material testing papers has been one of my research articles in material testing has been published. Okay, thank you.
Thanks for the wonderful session, sir.
Thanks, sir. So if any queries,
Thank you,
you
sir.
can raise.
Yes, sir. Yes, sir. We have already have queries. First, I need to thank you for this wonderful session, because in spite of your busy schedule, you have been doing this very good session. You have been doing this a very grand success. Before going to vote of thanks, we have questions from audience, sir. So the first question is being reason for choosing magnesium because magnesium and its alloy it seems to be costly nowadays. It can be optimized with a lot of alloys and we can do economical things, right? So
Yes.
that is what the reason for choosing predominantly we are choosing magnesium. So that's the reason we need to know.
So actually, mainly several engineering materials, most of the research and engineers are focusing on the lightweight materials. And some of the materials in magnesium alloy are widely used in the various applications like automobile and aerospace industry. So not only all the materials are very costly, some of the materials we can commercially available in the market. So it is our main motto is we have to modify the surface of the workpiece using EDC techniques because of I already showed in the ZD41 magnesium alloy. It is some of the applications also given in the slide. So by using the electrical discharge coating, what is the performance? Only sir, only study what is the performance after conducting experiment only sir. Actually, it is not commercially applied in various field of industry. It is still in under research only sir. Okay, sir. This is one of modification techniques only by using the magnesium alloys.
Thanks, sir. Thanks, sir. Another one question from the audience is actually what are the future scopes you have been planning with this topic?
So actually, I already told sir. Actually, it is an okay. It is an okay. Future scope means it is an being developed. It's improving, sir. Actually, so it is
Sorry for interruption. Sorry for interruption. The topic is being interested means. So that is what the students are expecting. The future scopes for the wide research areas means it will be useful for them to
okay.
conduct their future research works, right? That's why.
Definitely. Actually, so future scope is mainly already discussed in research articles. Future scope means application orientedly we can implement this process to biocompatible process, biomedical applications related, sir. So some of the applications practically applied. So you can see the biomedical application related articles you can see, sir. Okay.
Thank you, sir. Thank you. Thanks for the information and thanks for the clarification, sir. Now it's the time to deliver vote of thanks. Now I welcome Mr. Desigan, Assistant Professor from Department of Mechanical Engineering, to deliver vote of thanks. Please, sir.
So, good afternoon, friends. This is Desigan, Assistant Professor, Department of Mechanical Engineering, King's College of Engineering. I am very happy to deliver the vote of thanks on this event on behalf of Department of Mechanical Engineering. First of all, I would like to thank our chief guest, Dr. U. Ilarasan, for his excellent lecture on surface modification of magnesium alloy using electrical discharge coating. Then, I especially thank to our management for provide this facility for conducting this webinar. Next, I thank Dr. Rajendran, Secretary of King's College of Engineering, for his continuous support for conducting this type of events. Next, I wish to thank our principal, Dr. J. Arpuda Vijay Selvi, for his wonderful support and guidance. Next, I like to thank our vice principal, our HOD sir, and faculty members and other students from our college to support this webinar, to conduct this webinar successfully. Thank you once again. Thank you, all of you.
Thank you, Desigan, sir. We request our audience for any queries. Any queries from our audience?
Some queries, some students are posted their comments and related queries in YouTube website itself, sir. So
Okay.
after this session, better Ilayasans sir at 3 times they may come to the YouTube live comment session and better they will type the comment and answer them. That's all.
Fine, sir. Fine, fine.
Definitely, sir.
To all the audience, the feedback link has been posted in the live chat as well as it will be displayed in the descriptive session very soon. Please fill the feedback form within 30 minutes to 1 hour. It will be available in the description. No need to worry about it. Will be available in the description session. On behalf of Mechanical Engineering and King's College of Engineering, Punalkulam, Pudukottai, we thank all of our participants. We thank all of our faculty members and everyone. Thank you, sir.
Thank you, sir, for a wonderful opportunity for giving me.
Thank you, sir.
The coordinator of the program, Mr. Desigan, sir, Secretary, sir. Thank you very much, head of the department, sir, management. Thank you very much.
Thank you. Thank you. Thank you.
We have to thank more, sir. On this typical COVID situation, you accept our invitation and come and spend your valuable time. That's all. We thank you very much. Thank you very much, sir.
Thank you, sir.
Thank you, sir. Thank
Thank
you. Thank you, everyone. Thank you, everyone.
Shall I leave, sir?
Yes, sir.
Yes, sir.
thank you, sir.
You can
Yes, sir.
you can leave. Thank you.
You can
Thank
leave.
you.
Thank you, sir. Thank you.
சொல்லு திசீனு.
Please exit.
Oh,
Please exit. Please exit.
முடிஞ்சுதுடா.
Please exit.